probing star formation with Wolf-Rayet binaries.
All right, so good morning, everyone. My name is Rory Bentley. I'm a grad student at UCLA working with the Galactic Center group, and I'm here to tell you all today about my project looking at probing extreme star formation in the Galactic Center with Wolf-Rayet star binaries. So, in the Galactic Center, there is a population of young, massive stars within the central half parsec or so. Their origins, however, are unknown. A possible hint of their origins was found when it was discovered that a lot of these stars are located on a clockwise rotating disk surrounding the central supermassive black hole Sagittarius A star. This is what you'd expect with for a star formation model from an accretion disk around a black hole. But studies looking at a larger sample size found that perhaps about only 20% of the stars were located, of the young stars were located on this disk, which is a lot smaller than the star formation models, which predicted about 100% of the stars should be on the disk. One possible way to probe possible star formation mechanisms in the Galactic Center is through looking at binary stars. Binary stars could serve as a probe of interactions between the stars within the cluster. The binary fraction could also look at the outcomes of physics of the star formation. For example, if the binary fragmentation rate when the stars are forming is different than it is in the field. Additionally, unrecognized binaries could change the amount of stars that we assume are on the disk, as if they're the star is a binary, you're not only going to have the motion of the star around the black hole to consider, but also it's just the intrinsic motion from the binary pair, which could change the apparent velocity of the star along its line of sight and lead to a misidentification of a star as on disk or off disk. My project is looking at a systematic search for companions of Wolf-Rayet star binaries in the Galactic Center. For some context, Wolf-Rayet stars are a late evolutionary phase of some of the most massive stars. They're characterized by having very high mass loss and very high luminosities. They're also likely to have a very massive companion. So any radial velocity variations from these stars will be very high and thus easier to detect. My sample is looking at 26 Wolf-Rayet stars throughout the Galactic Center. We have a map of them here. And we have 16 with new radial velocity measurements in my upcoming paper, Bentley et al. 2024, along with 10 Wolf-Rayet stars that have multiple radial velocity measurements from the literature. I should note that 3 of the Wolf-Rayet stars in the Galactic Center have already been identified as binaries. These new radial velocity measurements were taken between 2006 and 2024, mostly with OSIRIS on Keck, but also with NIFS on Gemini North. This is part of the much larger Galactic Center Orbits initiative, looking at stars and physics in the Galactic Center. We have about 150 RVs from OSIRIS and about 30 RVs from NIFS. And then we augment this with another 61 radial velocity measurements from the literature, which actually go back all the way to, I believe, 1994. We have an example spectrum here for one of our Wolf-Rayet stars. This is from IRF 16C. You can see it has a big emission line. Wolf-Rayet stars principally actually have emission lines because of the hot gas streaming off from their winds. And this is just an example spectrum showing a nice bracket gamma line. So to identify RV variations, we do this by cross-correlating the spectra. This is just basically measuring the relative shift in wavelength between 2 spectra in order to identify relative changes in the star's radial velocity. We then identify binary candidates by looking for RV variations of at least 3 sigma. We also require that the RV variation must exceed a critical size to avoid contamination from wind-driven variations within the stars, kind of mass loss. Wolf-Rayet stars, they're kind of the structure of their winds that produce a lot of these emission lines do change somewhat over time, which can lead to small changes and kind of a wiggling in some of the emission lines. But the scale of these, of kind of this wind-driven variation has been quantified. So we know for different spectral types, like above, if we see some RB variation above some kind of particular scale, it's likely not due to the winds. We were able to identify two new binary candidates, which we see in the top two plots here, S8181 and IRS 1384. For a sample size of 26,
It's in the middle.
annoying. Let me see if I can move that.
There it is. Sorry.
All right, no problem. Okay, for a sample size of 26 Wolf-Rayet stars with multiple radial velocity variations, we're able to detect both the three known binaries along with these two new candidates for a total of 5 binaries or binary candidates. Simulating a population of several populations of Wolf-Rayet stars across different like binary fractions, we find that for a detection of 5 binaries, we would expect the total kind of population of Wolf to have a binary fraction of about 71%, which is consistent with the roughly 60 or 69% binary fraction that we see from O stars in young massive clusters outside the galactic center. Okay.
I'm gonna click on your slide.
There we go. Okay. Additionally, with our new radial velocities, we can also get new disk memberships for some of these stars. This plot is showing basically the orientation of the kind of inclination of ascent and inclination and ascending node of different of our Wolf-Rayet stars in the galactic center in their orbits around Sagittarius A star. The green contours show the 1, 2, and 3 sigma bounds of the clockwise stellar disk as identified with the values from Gia et al. 2023. The red dots with the names are the kind of inclinations and ascending nodes of the kind of binaries or binary candidates in the galactic center. And then the blue dots and contours are the inclination of ascending nodes of the stars, which we do not identify as binary candidates. One interesting thing to note is that actually all 5 of our binary stars are located off the disk. We can also use our new disk memberships to split the population into 2 groups, the on-disk and the off-disk population. We find no binaries on the disk and are able to place a binary fraction limit, upper limit, a 68% upper limit at about 43%. This is not a particularly significant result, though, because we only believe about 6 of our stars in our sample are actually on the disk. So although the binary fraction appears to be lower, again, there's a lot of, there's a small sample size. But it is kind of a hint at a difference potentially between the off-disk and on-disk population. For the off-disk population, we have 5 binary stars. When again, we find a binary fraction of 78 plus or minus 16%, again, consistent with field stars. Possible explanations for the differences in this binary, for the possible binary fraction difference between the on-disk and off-disk populations are 3-body interactions between the binary pair and the supermassive black hole. These 3-body interactions could lift the binary star's orbit into a different inclination and off the disk. But this is actually not favored due to the relative angular momenta in the binary pair versus its orbit around the supermassive black hole. Additionally, binaries could be disrupted due to interactions with other stars within the disk itself. If the binary stars will have a higher interaction cross-section versus a single star, which could lead to an increased rate of interaction, or binary stars simply may be different versus for on-disk versus off-disk population stars. This last point I want to note actually has there hasn't been much recent simulations of star formation in an accretion disk. So the most recent simulations have not actually included the effects of binary. So that's something that people could work on in the near future. finally, so binaries may be disrupted due to interaction with other stars within the disk due to its higher stellar density, as I mentioned before. Dynamical work suggests that binary stars that are closer together would be, when they interact with other stars within the disk, would stick together when they would stay together if in interactions that would lift the stars to a different orbit and off the disk. Whereas further kind of binary stars in a further pair would get disrupted, and you would end up with two single stars. This plot on the right shows binary semi-major axis versus distance from Sagittarius A star. Binary stars whose semi-major axis would lie in this band up here. The binary stars in interactions they would be more likely to unbind, whereas binary stars down here will likely stick together in interactions that lift the star. One of our binary stars, IRS 13E4, appears to actually be fairly wide. And so in this red area, which is estimated kind of likely range of semi-major axes for our binary versus its projected distance, versus its not projected, its possible distances from Sagittarius A star. We only know its position in the sky. We don't know its kind of line of sight position exactly. This is the first binary with a possible semi-major axis in this region where interactions would likely cause the binary to unbind. The fact that this suggests it could have formed in situ if it does have a higher semi-major axis, which would suggest it likely formed, it likely formed where we see it today, as interactions would unbind the star if it was lifted off the disk. Excuse me. Okay. With that, I will leave up my summary and take any questions.